but I watched the video and the fire alarm actually scared me.
Oh, no. No, that was during your clausura. You guys had the fire alarm?
No, that was in first hour, right?
First hour, okay. Super, good. Yeah. I'll tell you what, let's turn this thing back.
I think it's, oh no, that's NHS. I just need to get some signatures. It's due tomorrow. Yeah.
What?
I didn't know that. I thought it was due in a week. Yeah, I'm pretty sure it's due tomorrow. Mr. Rice, I'm applying to NHS. Could I have
course.
your signatures? That's
Sure.
from each year of community service.
Sure.
Next to your name.
So, boom, boom. Right here. And here.
I think that's
That's
all.
it. You sure I can sign a few more places too.
Thank you.
Is it tomorrow?
Hello. Ah, you're here for the snooper course.
Yes.
Great. Alessandra, I know you are.
Julia.
Thank you. You both can just sit probably in front because you know what? My person is not here today. So just sit there. That's great. Welcome, both of you.
Could you
Hold on. Yes? But not this second. Hold on, Kilpin.
Okay.
Can I see yours?
There's basically just community service board member, tutor, childcare, and then all like clubs open. Tutor is a leadership position.
Is it?
Yeah, you're tutoring someone. That's a leadership.
Morning, JFK. We have some announcements for you today. First, to all 11th grade diploma students, please check your email for important information from Ms. Basilico regarding 12th grade enrollment. Community service will be having another Shinnecock Park cleanup today, March 1st at 4 p.m. All students are welcome to make the park look good again. Mr. Rice will have plastic gloves and bags for you there. Meet in the park.
At the smoker spot. She didn't want to say that.
Congratulations, on accepting the fitness challenge to beat Mr.
Censorship,
Dillon in
sorry.
dips during sports class. Mika completed 29 dips in a row and almost beat Mr. B. Mika, a job well done. From Haywire, do you want to support the JFKS art scene? You come down to the first floor of Blue Building to buy the latest issue of the Haywire magazine. Magazines will be sold this Wednesday, Thursday, and Friday.
Thank you.
Each copy costs €5. See you there.
And at 1 o'clock.
And one more announcement regarding the upcoming spring play.
Rhonda, a tough woman, and Dave, a not-so-tough man who loves Rhonda, tries to show Rhonda his love, but she seems to be uninterested. Rhonda doesn't believe anyone can be interested in her. Dave tries to convince her by giving her an abstract painting he made. One thing leads to another, and if you want to know what happens next, you're in luck. Just next week, the Kennedy School Players present Almost Named. This midwinter night's dream is a bilingual English-American play filled with love, excitement, and lots of drama. Performance nights will be on the 10th, 11th, and 12th at 7 p.m. in the large hall. We are not charging for tickets, but donations are appreciated. See Kennedy School Player to reserve your seat today. We can't wait to see you there.
That's it for today. Have a great day.
Okay, so I'm missing Quinn. Tom is here. Well, let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Minus 3 is 8. Sure enough. Okay, I got everybody else. Okay, so welcome to my Schnupper people. Welcome AP folks. Although I feel like you're also on this side. I feel like I have to look this way. But anyway, at any rate, and feel free to move up. You guys don't have to be in the back there, Rhea, Aaron, Lena. You can actually move up and be, closer. You can certainly all move. That would be swell.
Was that an invitation or
That was
or a request?
Invitation, a request invitation. How about that? Thank you for moving back up. That's appreciated. We want to make our Schnupper people feel welcome as well. So, Schnupper people, here's the deal. I record these when I have folks at home, so you won't be on there, but my voice will be on there, and that's why I have this set up for the different hours, and I send it to folks who are sick at home. For everybody, we're trying to get wrestled through today and Thursday chapter 6 ideas as well as we can, so you guys can work on the chapter 5 and 6 problems while I'm gone on the 8th grade ski trip, maybe occasionally with my online help while I'm there. And when we come back, we'll hammer 7 and 8, which are fairly short, and I've minimized the amount of problems we're doing in 7 and 8. 5 and 6 are not so short, but they're important. Acids and bases are a crucial part of this course. So what I'll do, I think, today as an objective is I want to come back to this. This is used with something called titration, and I've left it unprepared to show you a couple things in it where students make mistakes. And by that time, I hope my online people are here as well so they can see this item. A burette is what this sucker's called. There's a bubble here. There's bubbles here. Not good. So we'll see why that's not good and what that means. Okay. Let's just take your questions and comments. Aaron?
Could we do number 4 of the lab, because I think a lot of us were confused on that one.
Absolutely. Okay. And I'll explain to the Schnupper people what we're doing. You had another question on the lab, Shilpa, or something else?
I was going to ask about 3. I already put it in, and I know it, but I'm kind of confused on it.
Well, here, you can get it back. I have not graded it yet, so if you want to look at it, that's fine. Okay. We had a lab on testing the pH of what, folks that were here? Testing the pH of what? What did we test?
Was it various salts?
Yeah, salts that had metallic what? So the pH, this is our lab, pH of salts with metallic, oh, good, Rhea. Cations, nice. So cations are positively charged. So the general thing is if we got something positive and we add it to water, it pulls off a from the water, just in a general way. Tom? No, remember, Tom, there's only OH minus or H plus.
It pulls off the OH minus.
OH minus, called the hydroxide. So I get like a hydroxide pulled off, so I get cation attached to like hydroxide. And that's OH minus for folks that are looking at the course. Plus, what's left when I pull off this, so to speak? Aaron, you got it. And that's what makes most of these what sort of pH then in this lab in general, Shilpa? Acidic. So we're talking about acidic salts. Why? Because these metal cations pull apart water and grab, as Tom described, the hydroxide, the OH minus, leaving these guys behind. So that makes it an acid. or using Sherry's, our book's author's terminology, that'd be H3O plus, right? Wouldn't it, folks, if we do it that way with her technology? Okay, let's take a couple questions. Do I have any extras to have you guys look at this? I think the answer is no, but I'll take a quick look. I do have one. You can share that and see kind of what they did. They made the solution, and then there's the backside where we tested them. Okay, number 3, Shilpa, what's up with 3?
So basically, I was looking at electronegativity.
Yeah.
Both elements, but didn't we say that electronegativity increases like furthest right upper corner of your table? And I looked it up online, and it was the other way around. So FE was actually higher. Is there like a reason for that?
Yeah, there is. So let's have a look. I think I talked to one of you about this, did I? So let's see. I'm not going to hit you. I'm going to point at the board up here. So the problem with number 3, everybody, is both aluminum and iron 3 have what charge? No, this is not a trick question, Sarah. 3 plus. So they're both 3 plus. So what you got to do, and I don't think it has to do with electronegativity necessarily, you got to think about their size. Okay, they're both 3 plus. Let's look at them. So there's iron and there's aluminum. Which one's bigger, iron or aluminum? Snipper people probably know too, yeah?
Iron is larger.
Iron is larger. So here's what that means. My folks, who will then pull apart the water more effectively because of that size difference? Think Coulomb's law when we talked about that. Shilpa.
Iron.
Iron, no.
Oh.
Why's it got to be the other? See if we can guess, Lena.
Because if it has like a shorter distance to the core, then it contracts with a stronger force.
You got it. So Coulomb's law said the longer the distance, the weaker the force. So if I'm this far from a water, I'm further. The nucleus is further from this sucker. But if I'm this close, I'm much closer, and that makes it much easier for this sucker to pull apart the water. So if you looked it up on the internet, let's see if this works with the internet answer. I hope so. So therefore, the one that will be more effective at making stuff acidic will be which one? Tom?
The aluminum.
The aluminum. So is that more acidic according to the internet? I hope. What'd you find out? Is that the one they said?
I'm not sure, but I was, because electronegativity value is like the ability to attract electrons, right?
Yeah, but you're not just attracting electrons. You're pulling stuff apart. And to be honest, electronegativity is pretty important with nonmetals, but these are metals. So I just would be surprised if it plays a role here.
But wouldn't it kind of, because the FE electronegativity value is like a lot higher than the one at aluminum, wouldn't that play some kind of role?
I don't think so.
Okay.
Because electronegativity is actually defined in a really strict way. You ready? Electronegativity is the ability of an atom with, Shilpa, a covalent bond to attract and pull the electrons in that covalent bond closer. Once this thing dissolves, I got an ion. I don't really have a covalent bond anymore except in the water. And you're not pulling electrons, you're pulling apart the water. So I think we got to go with a more common idea. And so if this is,
Would that be size to charge ratio?
yeah, so we can say, so Al3 plus is smaller and more, no, and has a greater, force essentially to pull apart waters. So I think the aluminum, and is that what it came out to our data on average? Was aluminum more acidic? No?
That's why I was confused because of aluminum. We had like all of this actually had like a lot more acidic than aluminum.
The aluminum was not very acidic.
It was like, so our average was like a 4.18 for aluminum.
Here, let's give me the two values. So for aluminum, pH was 4.18.
Yeah, as like an average, and for iron, it's 2.13.
All right, so I got to rethink my thinking. Obviously, I've done something wrong.
But that's the same thing that came out on the internet, that's why I was so confused.
What do you mean?
Like,
That's the
no,
same
no,
pHs.
No, when I thought about it like that, right?
Right.
Then I Googled it because it didn't coincide with the data,
Right?
but the internet said the same thing.
That
That the
aluminum should be, or the aluminum should be more acidic according to the internet.
Yeah.
In other words, there's something to do with our data being wrong. So in other words, Aaron, our data was wrong.
Okay.
I mean, no, I'm putting that out as a proposition. So let me make sure what everybody Googled. So you Googled the pH of these two ions and you found they had the opposite data that we got. Is that
Quinn
right?
just said something about F-check. He says aluminum hydroxide is way more soluble than iron hydroxide. Maybe that's what.
What?
Aluminum hydroxide is more soluble.
Okay, but I still got to get something straight with you. This is what we found, right? But my question to you to verify is what values of pH did the internet tell you? I thought that's what you Googled. Did anybody Google that? Because if you don't, I will, because that's what we really want to know. Is our data right or is our data wrong? So if our data is wrong, then my explanation might be right. If our data is right, then my explanation is probably wrong. Yeah, okay, so let's try that. I've done this lab often enough. I don't remember this being a problem, but let's just find out. So you guys can Google too. Could you help me do this? pH of aluminum ion solutions. All right, this is about plant roots, but they got it about 4.7 for a pH. And what did we get for aluminum? So hey, look at that. We're not really all that different. Let's try the iron 3 ion.
I mean, according to the internet, the pH of iron is just less than aluminum. Or the other.
So 2.85. And this was 4.7. So in other words, the internet data agrees with our data. Am I right so far?
Yes.
Okay, so therefore my explanation must be baloney. So let's figure out together a new explanation. I really thought it had to do with distance to the charge, but it's something else. So let's try and figure it out. Suggestion, Shilpa?
I mean, for me, what I said is, because I looked this up online and it said the acidic solution of the metal ion is related to its ability to attract electrons or the charge on the metal ion. And since the charges are the same, you probably want to look at the electronegativity, which is the ability to attract electrons. And then the values online said that Fe has a higher electronegativity value
Then aluminum.
I mean, I would say that's a reasonable, like,
I mean,
I don't know, but
Yeah, you're defending your logic well. So I could be wrong, even though I've never really thought about electronegativity, because this is usually something in covalent bonds we're talking about. But if that's the explanation, we'll go with that. I have an alternate too, which I'll throw at you. but leave that. If that's what you came up with, you're defending it well, go ahead and leave it. Good, Shilpa. No D, then I'll get to Tom and everybody else.
The point you made about its size,
Yeah.
and what that has to do with it, I assume that still plays a role, but maybe its size affects its electronegativity. So I mean, the idea that I used is that since iron 3's electronegativity is higher than aluminum's, it pulls off more OH minus, meaning there are more H pluses left over. And then obviously that makes it more acidic. I mean, could you explain like what electronegativity means in terms of covalent bonding? Because I don't really understand that yet.
Okay, if I'm bonded to, I better go back to my live stream so I can see if anybody joined us. No. If I'm bonded to the atom here and I have a greater electronegativity, then I pull the electrons in that covalent bond towards me. That's what electronegativity is. So I'm not familiar with the idea with ions that are floating in a solution being electronegative, especially if they're cations and they're positively charged. I don't really get that. Other than the fact that maybe they're saying, and Shilpa, I think what you've said is their attraction to electrons. So if that's the case, then Fe has a greater attraction to electrons because Shilpa's looked it up. It has a higher electronegativity. So maybe that's it right there. And I'll take other comments and then we'll go to another possible explanation. Tom.
I think maybe Quinn's idea from earlier might apply. He said that the solubility of aluminum hydroxide is much higher, so I guess maybe when this FeOH and OH3 and ALOH3 form, the ALOH3 molecule will decompose pretty quickly.
They're not decomposing, they're floating in the solution, right? Like if it's soluble, then I got a lot of these floating in solution. But to me, Tom, that would mean it would be more acidic, not less. I'd have more of these suckers that would be formed. So I think if Quinn's arguing solubility matters, I don't think that's true. I don't think that's true in this case. Other idea, Aaron?
Not really, but like, what are we supposed to write down?
We're getting to that. Okay, no, Aaron, your point is well taken. And I do want to wrap this up because we have a lot to do. Okay, so here's another explanation, although I'm comfortable with Shilpa's explanation because now that I think about it, it's making sense, even though it's not a way of thinking about electronegativity that I know about. So if you want to talk about the difference in electronegativity, write that, Aaron, as your answer. That's fine. Here's another way to think of it. I don't know if it's right or wrong. Which one has a greater surface area? Which ion? No, B. Iron. Sometimes the size matters in terms of how many waters I can pack around that sucker. Like, which one could I pack more waters around to break up? The iron, exactly. So sometimes it's that. Why does that bother me? Because I'm still got a greater internuclear distance, but maybe it has to do with the size. And if that's the case, another explanation, and I don't know which is right, Shilpa, yours may well be the right one. Another explanation could be the bigger the size, the more waters could be, because of the greater surface area, the more waters that could be pulled apart around that bigger ion.
What was Shilpa's explanation?
Shilpa, you want to summarize your explanation again?
I looked up like what's related to the acidity of the solution, and the acidity of the solution of the metal ion is related to its ability to attract electrons, which is electronegativity, or to the charge of the metal ion. And since I'm not going to charge, so you would want to look at the electronegativity, and I just looked at the values, and the one of Fe is higher. So it makes
The
that
thing is, it's not by a lot. I think it's by 0.2.
That's like a lot in the standards.
Yeah, in the standard, I think it's plenty. So if that's the case, let me think of another way of thinking of electronegativity. Perhaps it's also the ability to pull something that has electrons like OH minus, we talked to Tom about earlier, to pull that towards the ion. So if it has a better ability for whatever reason to pull OH minuses towards it, then of course that'll break up more waters as well. So thank you, Shilpa, for your research on that. Well done. Questions, comments from others? So either of those explanations I would find fine. That's for sure. And we want to talk about number 4 as well. So number 4, this one's a lot more straightforward. It's trying to be tricky, but I know Tom at least figured it out. Let's read it and see if others figured it out too. So Tom, could you read number 4?
Yep. Oh, right, the question.
Yeah.
Iron pipes are often used to transport water underground and buildings. Would you expect this water to be very acidic? Why or why not?
And Tom, why don't you go ahead? What you say?
I said no, because the pipes are not built out of ionized material, built out of metallic. Fe.
Good. Yeah, they're metal atoms. They're not metal ions that are in the pipes. So
Yeah, I said no, because iron pipes are not built out of ionized Fe. It is kept in metallic bonds.
What are metallic, like,
metallic bonds are the bonds between the metal cations and the free moving electrons that are around them. But instead of them being separated, I got metal ions in every direction, Noah, connected to each other and make up every chunk of metal in the world. And it's a very strong bond between the Fe, whatever it is, 2 plus, 3 plus, I don't care, and these free moving electrons that move around the lattice. Think about moving around a three-dimensional hunk of Fe3 plus ions, and they just, like a glue, keep the whole thing tight together.
does that make a metallic atom? Like,
Makes a metallic molecule.
okay.
Like this sucker, that's one molecule. And it's all tightly pulled together by these metallic bonds.
Doesn't iron corrode though?
Yeah, once it corrodes, but I mean, this is aluminum anyway, and it's not corroded. And if we got iron pipes and they're not corroded, then we're okay. If they're corroded, you got another thing coming, because then they fall apart anyway. Yeah, but if they're just iron pipes, that alone is still okay. Okay, good. Other questions on the lab? If you're done, I'll take them. If not, give it to me on Thursday, okay? And Quinn or whoever else out there who did the lab, send it to me if you want to. It's up to you.
Okay.
All set?
We're on the top.
That's fine. Thank you. And there's, like I said, if not, I'll keep them Thursday. That's fine. Okay, so we're going to change gears now. And thank you. We're going to change gears now, and I think do this. Let's take your questions, and then 7th period, we'll start to talk about this item right here. Thank you, Tom. So do you have questions on chapter 4 or 5? What are we on, 5? At this point, anything you've hit in acids and bases you'd like to ask about? I know some of you are looking at me like, I'm still on chapter blah, blah. Oh, God, I know. And I'm sorry to pressure you so much, but this is the time of year when I've got just a lot of work for you. And I'm sure you do in all your classes, but try and crunch through 5 and 6 while I'm gone. So it's a tough time of year for AP Chem.
Oh, I
Shilpa?
think you just answered my question, but when you're gone, are we just gonna be catching up on 5 and 6, or are you gonna be working?
You're going to be working on 5 and 6 while I'm gone.
Okay, so
I'm not going to lecture on anything new because I can't really do that from the 8th grade ski trip. I don't see myself being effective doing that. I'd love to, but I don't think that's going to work. I have too many little tiny screaming people that I have to take care of too. Not that you were ever like that. Never mind. No, deep.
As we're now getting dangerously close to the AP exam, what do you suggest we start? Because if I'm being honest, like I haven't started specifically or exclusively preparing for the the exam yet. What do you suggest that we do?
Okay. Ultimately, there's two things going on. Ultimately, all your book work will be due on the day of the exam, which is like what, May 4th or something like that. Unfortunately too, April 4th is our clausura. And I need you to get through at least the ideas, even if you don't get the problems done. You got to get through the ideas in chapter 7 and 8. So maybe get through the ideas, and I'll help you do that as soon as I get back from the ski trip. And then just start grinding through the material. Now, in terms of my clausura, I don't know if you'll be able to get to that review program that I sent you and everybody know through the Google Classroom. If you can start to review that, that's probably great. If you take one night even and read through the whole darn thing, it might help you review and help for the clausura. Certainly you want to go through that review document before the test, if you're taking the test in early May. Yeah. Mhm.
Is the idea that if we understand like every single thing they bring up on that review, we know everything we need to know for the AP exam?
Everything is a big word. I'd say you're well prepared for the vast majority of stuff that will be on there, yes. The vast majority. Every little thing, sometimes they surprise me with a detail or two that I didn't really teach. But most of the stuff I do, and you'll be prepared. The other thing I hope when we get through 7 and 8 is I usually have a week or two at least for you to work some old problems in class. Like the first period, we might do a 45-minute exam, multiple choice, and then grade it and look and see how we can improve during the second period. Or part of a FRQ exam, and the next period we look through it, grade it, and see what they wanted, what they expected for getting the points. And I'll have the expectations. I have a list of those for how they give the points, so you can kind of see how the tests are built before you take the one in May. Nobi.
I don't know if this question is gonna make much sense, but if we're like relatively weak in FRQs, how much can our multiple choice section make up for that? Like,
It's only half and half, so you can't be that weak in either one. So you're gonna have to work more. If that's your deal or someone's deal, work on the FRQs more. If you're more uncomfortable with them, do more of them. And there's resources out there, and I've got resources. Even if I don't like, I've got more old tests than you can shake a stick at. So any FRQs you want, I can give you more to practice on for sure. But if that's any of you what you need to do more of, then by all means do that. Sure.
Is this clausura in April based on old AP questions, AP exam questions?
The
or is it-
clausura will be an old AP test. Yeah. That's how I do it. Okay, so Ute, all righty. Then if I don't have questions on the chapter, we're going to start back up with buffers. So when last we met, so find your notes if you would on buffers. And I know snooper people, this is probably a new word for you. Somebody who was here, just in general language, explain what a buffer is. What the heck was a buffer or buffered solution? It's not a vampire slayer or anything else. Have you had them before? Go ahead.
I
You
haven't,
listen.
but I guess it from the context of reading your exercise sheet. I would guess it's the solution that has been registered to be a certain value or a certain
Yeah,
pH
for the
level,
what? For the pH, right.
that we know its pH level, so we can test our instruments against it and to figure out if our instruments are actually accurate or not.
You could do that in test your instruments, but there's another reason for having pH. You're right about the solution. So folks that were here last time, we had a pH, well, we made a buffer, and then how do we test it? What did we put in and what happened to the buffer when we put, what did we add to it, Lena?
We added a drop of vinegar.
Yeah, when we added what other stuff to our buffer?
Was it HCl?
HCl, which is a strong
Acid?
acid, and we also added to another test tube, NaOH, which is a strong base. So if you have a buffer, even if I add some drops of strong acid or base, what happened to the pH? Noah B.
It would like stay the same.
It stayed the same. The color of the universal indicator, which indicates our pH, stayed the same. What happened when I did the same thing to water and I added a few drops of strong acid or strong base? You can just about guess what would happen, Alessandra?
Well, it changed.
Yeah, in fact, what happened to the values, Rhea, you weren't there. Were you there last time? You weren't there last time. Shilpa, when I added the strong acid, what happened to the pH based on the color?
Became less than 7.
Yeah, it became less than 7. It became a red color for universal indicator, which you might or might not remember last year, Alexander. That was like an acidic color. And when I added, Sarah, the strong base, I got what color? Blue. So water changes really easily. It's not a buffer. And why do we use buffers in terms of products? What practical use are they? Back to no B?
Well, we mentioned also like skincare products, they want to match the pH of, for instance, your skin or your hair, for shampoo and stuff. So I assume to not like irritate your skin.
You got it. So we want to match the pH of some other system. Or what about medicines? Shilpa?
There's aspirin because some people are intolerant, I guess, to extreme acidity in aspirin, so it decreases acidity.
You got it. So buffered aspirin has less of an acidic problem with our stomach. And if I have a medicine that I'm injecting into somebody's bloodstream, probably I want the medicine to have about the same pH as the blood. Exactly. So we match the pH to whatever system you want. And that's what I'm going to show you now and next period probably, because we won't finish. I want to give you the handy dandy buffer formula and show you how to use that to get the pH you want from a system. Okay? All right. So let's do it. So these are resistant, highly resistant to changes in pH. Okay. Here's what we're talking about. Usually, we have about equal amounts to make one. About half of a weak acid and half of its base. What's the word there, Sarah? Good. So conjugate means like matching. Snooker people. Half of the conjugate base. Okay, the weak acid we're going to call HB. B can be like anything. It doesn't mean boron. And the base will be AP, folks. Can you guess if that's my acid, then the base will be what, Tom? No, not BOH. That would make it a strong acid. Just B. Shilpa? Minus. There you go. So it's B minus. So there's our two conjugates, okay? HB and B minus. So we got about half of one, half the other. And you might say B minus, okay. Often what's happening is the B minus is attached to something like Na plus, something that is a spectator and doesn't really do anything. So in NAB, for example, all right, you know what I'm saying? So we got like a salt, NAB, and we had half of its conjugate acid, and that ends up, that's what I did to make a buffer last time. Remember I made one with the stuff in vinegar, acetic acid, and sodium acetate. Those were the two things I threw together to make my buffer that we tested last time. And I'll just say that. Okay, so Why? Why do you need both? Okay, let's have a look. So I'm going to take some HB and I'm going to add some OH minus. That could be from a strong what? My OH minus would be coming from a strong Tom? Strong base. Good. What will happen? Can you guess? So if I add this and this, what will form on the other side? Aaron. H2O. Good. The H plus comes off of here. Attach it to the OH minus. I get H2O. And then what's left, Aaron? You got it. And she might say, yeah, but we had a reaction. But look, all I created was water and B minus. Directly, I did not create any H plus or OH minus. In fact, I used up the OH minus. That's what a buffer does. It pulls out what affects pH and gets rid of it. What if I add to this something acidic? So let's just say we add a B minus. We have some B minus in my solution and I add an H plus. Or the Cheryl way I put in parentheses here, she would have it like that, wouldn't she? Okay, if I just add B minus and H plus, what am I going to make on the other side? Just throw it together, Sarah? HB. And that itself is not a strong acid or a strong base. In fact, it's a weak acid. And it doesn't really affect my pH very much at all. Or if I use the Cheryl method, this is kind of beautiful. Look at this. HB plus what's left then, so to speak, Rhea?
Water, H2O.
You got it. Yeah, and look at neither of those affect the pH directly. I know there's HB or B minus, but those are indirect effects. That's why the pH changes only a tiny, tiny bit. Still nobody there? Well, so be it.
I'm pretty sure Quinn is there.
Well, if you're there, Quinn, say something. I asked him to say something, but nobody has, so maybe they couldn't make it for some reason.
He's texting like that himself, he can't. Because sometimes there's problems with commenting on the live stream.
Oh, okay. All right. But he was able to comment a couple of times ago. That's why
Yeah, she just said something.
we did. So somehow I'm not seeing it. Oh, okay. Quinn, hi. Okay. All right. Let's talk about the weird but true buffer facts. The buffer facts of life. Yes, I made that up. And there's two of them. So one is, you can assume equilibrium is established without appreciably, so without very much, changing the HB or B minus concentrations. So what am I saying? So I'm saying that the HB that you have is usually pretty much the same as the original. The O stands for original. And same with the B minus. The B minus concentration is pretty much equal to the B minus original. Well, what does that matter? Okay, so let's go to weird fact 2. Since HB and B minus are in the same container, the ratio of their concentrations, you'll see why that's important in a second. equals the ratio of their number of moles. And this sucker, I'm going to put a star by because it's really beautiful and really useful for us. Okay. Let me make a little space here. Okay, time to give you the handy dandy buffer formula. Are we ready? That's not, because I need people to see that. Hopefully people can see that at home. Okay, so. No, I don't want to put even original there. Or the pH equals the pKa plus the log of this big sucker. The log of the upside down now, B minus concentration over the HB concentration. It's got to be upside down because of some laws of logs. I don't know why I have a hard time memorizing this one, but I like this one. Anyway, one or the other of these, they usually give you on the AP given information sheet, and we'll have to see what they're giving this year. That's a good place to stop. Thank you, Snooper people, for joining us. Super.
Could you possibly show us the history of like the courses and information? Like sometime, not necessarily now.
Yeah,
One day.
one day. Maybe I'll just send you one. Okay, I'm going to end this, and I'll be back again with everybody 7th period. So see you then. Sorry if you can't write.